Well, let me say just a little bit about the orientation of hair cells in our sensory epithelium, because this turns out to be quite important for understanding the function of each of our sensory structures in our vestibular labyrinth. For the otolith organs, what we find are the hair cells are arranged with a certain axis of symmetry that divides the sensory epithelium within each of our otolithic organs. So, for example, notice here in the saccule, so this is the sensory epithelium in the saccule. This is called a macula, meaning a spot. So there's a special sensory spot in each otolith organ called a macula. And these arrows here are meant to illustrate the axis of symmetry of the hair cells. Now notice that in the saccular macula, there is an axis of symmetry that sort of runs right down the middle of this structure. And the hair cells are organized from shortest to longest going in opposite directions. So the arrow points towards the longest stereocilium. So this means that if we're going to deflect these hair cells along their axis for depolarization or hyperpolarization, then this saccular macula would need to be rotated essentially along the y-axis, which means the saccular membrane is going to be sensitive to deflection that would either pitch the head in a forward tilt or in a backward tilt. Also, the accelerations up and down that we would experience in an elevator would also be expected to be in line with the orientation of activation that we find here in this saccular macula. Now let's look at the utricle and its macula. Now there is also an axis of symmetry here, and there's a bit more of a curvature to this axis, and what we find are that the hair cells are arranged basically with the opposite kind of polarity. That is, the longest stereocilium is towards the line of symmetry, with the shortest being peripheral to that line of symmetry. Now, this utricle macula is largely in the horizontal plane. Not entirely, there's a little bit of it that curves upward, but it's largely in the horizontal plane, while the saccular macula is largely in the vertical plane. So this means that this utricle macula is going to be most sensitive to linear accelerations that we might make with our head in the horizontal plane. If we were to tilt our head to the left or to the right in this sort of a rolling action, if we held that tilt, what we'd find is that it's really this utricle macula that is most sensitive. And again, it has to do mainly with the fact that these hair cells are going to be activated because of the axis of depolarization and hyperpolarization would be activated as we tilt our head from one side to the next. Okay, so that's a bit about the organization of the hair cells and the otolith organs. We'll come back to this. What about the semicircular canals? Well, the semicircular canals are a bit more straightforward. There, the hair cells are found in these bulb-like structures that we find in here, and these bulb-like structures are called ampullae, or ampulla for a singular bulb. And within that ampulla, there's a sensory epithelium. We call that a crista, and that's where we find our hair cells. And in each crista, the hair cells are arranged basically just in one direction. So unlike our otolith organs where there's an axis of symmetry, there's no axis of symmetry in the semicircular canals. Within that ampulla, along that crista, all of these hair cells will either get deflected together in one direction towards the longest stereocilia or away from that longest stereocilium. Towards the longest is depolarization, away would be hyperpolarization. Now, I want to talk about each of these classes of organs and consider how the biomechanics of their function relate to the sensory transduction mechanism. And let's first start with our otolith organs. So here again is the macula of the otolith organ, and let's just say that this would be the macula of the utricle. And what we find is that these hair cells are not just projecting out into the endolymph, but rather there's a gelatinous membrane that sits right on top of the apical surface of this sensory epithelium. And yet on top of that gelatinous membrane are these calcium carbonate crystals that we call otoconia. And otoconia quite literally means ear stones. So we have basically a layer of calcium carbonate crystals. We can think of it really as a layer of pebbles that are sitting upon this relatively dense, relatively heavy gelatinous mass. So what would that mean if we were to tilt our head in one direction or another? Well, when we tilt our head, we're going to shift the distribution of that otolithic membrane relative to the fixed structures of the sensory epithelium. So if we have a static tilt, let's say in the backward direction, go ahead and tilt your head back if you like, what we find is that this gelatinous membrane, with the weight of it being pulled by the force of gravity, we find that that membrane would begin to slip in the downward direction relative to the fixed sensory epithelium. And the result is that the hair cells are going to be bent in the downward direction. Now remember the axis of symmetry that we found. So in this illustration, the hair cells that are here to the right are going to be T-polarized because they are being deflected towards their longest stereocilium. But the hair cells on the opposite side of the axis of symmetry are going to be hyperpolarized because they're going to be deflected away from their longest stereocilium. So within each macula of our otolith organs, half of the population of hair cells will be activated by a static tilt, whereas the other half will be deactivated or hyperpolarized. So this is not unlike the situation we talked about in the retina, where for the spot of light that strikes the retina, half of the population of ganglion cells for which that spot hits the receptive field will turn on. Those would be our on-center cells, and the other half will turn off. Those would be our off-center cells. So we can think of this symmetry in the macula of the otolith organ as being somewhat analogous to the on and the off structure of receptive fields in the retina. Only here now, rather than there being a physiological explanation, there's really a biomechanical explanation. The on and the off, or the hyperpolarization and depolarization, simply has to do with this axis of symmetry that runs through the membrane. Okay, well, let's consider now what happens when we accelerate our head in addition to when we tilt our head. So this would be our resting posture with the gelatinous membrane and the otoconia right on top of the otolithic organ. So our hair cells will be in a neutral position. And what I just described for you is the impact of that backward tilt. So now you're familiar with the idea that gravity would pull that otolithic membrane, and there would be a shearing force that would depolarize half of the hair cell population and hyperpolarize the other. Well, we can also activate this system if we accelerate our heads forward. So if we start walking, for example, or just lean forward with our head, basically what we're doing is that we are accelerating the sensory epithelium, and that will shear against the otolithic membrane because of the inertia that we would have as these membranes slip past each other as we accelerate the sensory epithelium, which is of course fixed to the bones of the head. So forward acceleration would be similar to this backward tilt, at least for this sensory epithelium. Now, movement in the opposite directions would be expected to produce the opposite physiological results. So a forward tilt of the head would result in gravity tugging forward that otolithic organ, and now that sensory epithelium should show the opposite physiological response. Now the hair cells that were depolarized by backward tilt will be hyperpolarized by forward tilt, and those that were hyperpolarized by backward tilt are now going to be depolarized. Likewise, when we decelerate, so if you're walking and you come to a stop, now what's happening is that this sensory epithelium is decelerating, creating a shearing force against the otolithic organ, as the forces of inertia eventually allow for the stabilization of this membrane back in line with the neutral position of the hair cell stereocilia. So deceleration is going to be similar to activating this membrane with a forward tilt. Now let's look at the physiological responses of the actual cells that are giving rise to the signals that can be recorded in the 8th cranial nerve. So if we were to tilt our head forward, what would happen is that there would be a significant elevation in the firing rate of axons in that 8th cranial nerve as long as we sustain the tilt. And the reason is simply that as we start that tilt and then maintain it, gravity has now pulled that otolithic membrane forward relative to the sensory epithelium. So these hair cells maintain their deflection of the stereocilia towards their longest stereocilium. That would be consistent with depolarization, so this would be a recording from an axon that innervates such hair cells on one side of that axis of symmetry. So these cells fire tonically, so we call this a tonic or sustained pattern of activation as long as the head is in its tilted position. And when we restore our head to neutral, then the firing rate returns to rest. Now if we were to tilt in the opposite direction, the very same axon would be expected now to decrease its firing rate. And that's exactly what happens. So if we're recording from the cell that was activated by a forward head tilt with the backward head tilt, then that neuron is going to have a decrease in its firing rate. So it makes some sense then that there ought to be a fairly high level of spontaneous activity in this system, because otherwise it wouldn't be possible to decrease the firing rate if the firing rate were already nil. So having some significant measure of spontaneous activity allows this system to either be increased or decreased, depending upon the deflection of those stereocilia. Okay, so again, let me just emphasize the major physiological point that I want you to take away from this, and that is that when we move our head by linear acceleration or by tilt in the vertical plane, we are largely going to activate our saccule. And this is again because of the orientation of the sensory epithelium, which is largely in the vertical plane, but also the direction of organization of those hair cells. So static tilt forward and hold, and backward and hold, or a elevator type acceleration up and down, that's going to activate these hair cells that are otherwise in this direction. In the same way, the macula of the utricle is arranged to be sensitive to motions in the horizontal plane. So linear accelerations forward or to the side, as well as head tilt and hold to one side or the other, is going to activate the utricle macula more so than the sacculus. Now, like most complementary systems in neuroscience, there is some overlap, so we can expect that any one kind of head tilt or any one kind of linear acceleration is mainly going to activate one kind of membrane or the other, but the other one will contribute to the sensations that are derived from that movement to some degree. And certainly if we move along some oblique axis of acceleration or some oblique direction of tilt, we can expect both otolithic membranes to contribute to the sensations that are derived from that motion.